Welcome to all of you. My minimum goal was to have at least one person here, and we seem to have overachieved that. So that's fantastic. Test-driven data analysis. What I'm trying to do with this is to make it very hands-on. There are exercises to do. If you haven't downloaded the stuff already, there are pointers on the slides to doing it. There were some handouts, which some people have got, but some people haven't. But I think there are pointers on the slides to them. They're all available online. So what I guess I'm planning to do is to talk a little bit about what test-driven data analysis is, in case any of you haven't heard it yet, which might well be the case, and then talk through the two main ideas, or the 2.5 main ideas in it, as it is today, and try and get you actually using the TDDA library that's available both on PyPI and on GitHub, if you prefer source. You are welcome to try that obviously on your own data, or there is test data provided with the library that you can work on, and I've kind of assumed on the slides that's what you're doing, but you're obviously welcome to do whichever you want. Do ask questions, do dive in. We don't have an enormous amount of time, but I think it's more use, probably if you haven't understood something, someone else won't have understood it as well, so it's probably much better that you ask. I suppose I should possibly just give 30 seconds on myself, which is I've been doing data analysis for about 30 years now, and I have a tiny data analysis company based up in Edinburgh, which is lovely. We do consulting and software. So we have commercial software, which includes all this stuff, but obviously also the open source library, which I'm talking about today. So everything that I'm talking about today is MIT licensed. You can do it, you can contribute to it. Love to get feedback, bugs, pull requests, contributions, any of that kind of stuff. Really hope you can use it and get some value out of it. These slides, incidentally, there's a URL on the front there. You can pick them up if you want to, and that'll appear a couple of times later on as well. TDDA.info is a blog that talks about all these ideas. So test-driven data analysis, it probably won't surprise you. The idea is to take the ideas from test-driven development, which is the sort of common center, I would say, to all the agile approaches to software development that aim to help with software correctness, and to take those ideas and adapt them and apply them to the area of data analysis. Data analysis broadly, any kind of data transformation that you might be doing. And I guess the thing that makes it interesting is that whereas with software you're primarily concerned with correctness, and we're certainly interested in correctness with data analysis as well, I think with analysis it's harder, because as well as correctness we need to be worried about the meaningfulness of the analysis. Are we correctly applying meaningless algorithms or inapplicable algorithms to our data? We have to be concerned with the correctness and validity of our input data. So it's, we're not really doing our jobs as analysts, I would say, if we just say, you give me garbage in, I'm going to give you garbage out. We kind of have to take responsibility for trying to make sure, as far as we can, that things look okay. And perhaps most difficult of all, we also have to, as far as we can, take some responsibility for the correctness of interpretation, at least in the sense of making our outputs as clear as possible and making it as hard as possible for people to misinterpret our results. Is anyone here not familiar with test-driven development? Has anyone not heard of test-driven development? One hand. Okay. So very briefly, test-driven development is the idea that the historical software development process basically consisted of, first of all, writing a specification for software, and then writing a design for software, and then writing the software, and then at the end of the process, writing some tests to try and make sure that the software actually worked. And test-driven development is the idea that you turn that around completely, and before you write any software, you first of all write tests for the software that say what it ought to do. So if you're writing addition, an addition function, you at least write some stuff that says, when you add 2 and 3, that should produce 5, and when you add 3 and minus 3, that should produce 0, and so forth. And you write those tests before you write any software, and you write them in a runnable form. There are frameworks out there that allow you to write these tests, run them, have them fail because you haven't written the addition function yet, and then then when you write the software to actually implement that addition function, hopefully the tests pass, or in practice what really happens is you discover that your tests were wrong and you modify them. And the idea with test-driven development is that you keep running these tests all the time on fixed sets of data and possibly on variable sets of data. And this has turned out to be, I think, a much better way of doing software development, a much more productive way of doing software development. And it's not we're not so concerned about the order of things here, but we're concerned here with trying to get the answer right, with right in the most general sense possible. Meaningful answers, answers that are actually going to add value, answers that are actually going to be useful to people. So the diagram that I usually use to illustrate this starts off with almost all data analysis projects, in my experience, start off looking something like this. There's some kind of a development phase. And in the old days, it used to be that was pretty much the only phase there was, but typically there's a deployment phase now as well. And during that development phase, we almost always use some kind of initial sample of data to try and make things work. And I guess in thinking about test-driven data analysis, what we've been thinking about is what are the things that can go wrong in this process. And the first thing that can go wrong is when we choose our approach, we can fail to understand the data, we can fail to understand the problem domain, or we can fail to understand the methods well enough that we're thinking about using in solving the problem. And if we get any of those things wrong, clearly we're very unlikely to get our analysis right. And we've sort of come up with this taxonomy of that, whereby we call these different kinds of errors different things. So we call those errors of interpretation, where we've failed to understand something fundamental about the problem right at the start. And so clearly we want to avoid these errors of interpretation. Having done that, when we're developing our analysis, and I'm using the term analysis very broadly, it could be building a self-learning live recommender system or credit scoring system or something, or it could be summing the salary bill or something. Or basically anything that involves taking data in and producing a result that we would think of as any kind of data analysis. So the next part is, once we've decided what we want to do algorithmically, how we want to solve this problem, tackle this problem, then we have to implement that in some way. And I don't necessarily mean writing code per se by this. This might be, running R or SAS, or it might be, typing things into Excel, or it might be using a GUI, or it might be actually developing Python code with pandas and, libraries and all this, or bokeh or whatever. But whatever it is, there's we go from the stage where we haven't got our analytical process in code to the point where we can do our analysis. And that's what I mean by the development of the analytical process. And the bad news is that it's possible to screw up there as well. So it's possible to make mistakes during I'm calling it coding, but in the process of doing the first actual instance of the analysis. And just because we like calling them all error of something, we call that an error of implementation, but there's a more familiar word for that. That's just a bug, right, in conventional software terms. And in terms of our sample data, pretty much if we get the approach right, if we choose good algorithms, if we understand our data and we implement it correctly, then hopefully we'll get some initial success. We'll get, whatever it is on our sample data will now be right. We'll have summed the salaries correctly, or we'll have built a useful model, or maybe not even a useful model, but at least a correct model, a model that's doing what it's supposed to do. And so that's our kind of initial success. And it used to be that that's pretty much all there was to most modeling. But I don't know about you, but what I find these days is that there's almost always an operational phase as well. So whereas it used to be that as consultants we would go in and we'd build a model for someone and we'd hand it over. We'd either hand over the scores or we'd hand over a specification of the model, and someone else would then be responsible for implementing it. Typically these days there's now an operational phase. It's not enough just to build the model. We have to set the thing running, make it so that it can be used continuously to make recommendations or to produce credit scores or to figure out who's at risk of churning, or whatever it is. And very often there's a self-learning process in there as well, where the model has to update itself, or at very least a monitoring process where it can figure out whether it seems to be behaving correctly. And the bad news is that there are lots more opportunities to get things wrong during these phases as well. So if we've developed our analytical process and now we want to feed a new data set through, we want to, credit score a new person, or we want to, add up this month's salaries rather than last month's salaries or whatever, we now have to run it. And it's possible to use this. I'm assuming we've captured this analytical process in some way in software, and because we now have to feed the data in, it's possible to screw up that part of it. And it's maybe even more likely that we'll screw it up if it's actually someone else, or it's a month later, and the time you've written it, you kind of know how it works. But when you come back a month later and you look at your immaculately documented code and the pure logical arrangement of the whole thing, maybe it turns out you can't quite remember quite as well exactly what all the magic you have to do in order to use the software correctly is, even just at the level of what switch to use or what order the parameters go or whatever. So, and when that happens, we call those errors of process, because we like this error of theme. And then if that goes okay, or even if it doesn't go okay, we then run our process and it produces the results of our analysis. It produces an analytical result. And a subtler thing can go wrong there, which is that there can be a mismatch between the data that we're now feeding into the system and the data that we originally developed it with. So basically the assumption, we're always making assumptions about the domain and the data when we build some kind of an analytical process. We have some idea of what the data is going to mean. And that's not a flaw in our analysis. Analysis can't work if we don't make any assumptions about the data and about the domain. But if the data that we develop it on is very different in some way from the data that we end up running it on, we can end up with an invalid model or an invalid calculation, or at least a model that's not going to work well because, a classic example of this is credit scoring, where you build a model on one population, then over time you start using it to score a different population. Historically, an example was most credit models were built on men, and then when banks started lending to women, the models weren't built on a female population, so potentially their characteristics were very different. It can be anything like this, just a difference in the distribution of the data that's coming in. And so if that happens, then potentially everything's working correctly, the algorithms are working correctly, the model's doing what it's supposed to do. It's just that now we have much less confidence in the outputs. And we call those errors of applicability. And then the final thing, and in some sense the worst thing of all, is at the end of it we have to interpret the analytical results. And we can get that wrong too. We can misunderstand what it is. So if we code the model, hopefully we understand what it means. And this can be, this cannot be a subtle thing at all. This can be an incredibly fundamental thing. Like, we have a thing, we have some system to say whether it's safe for an aeroplane to take off, and it comes out with 99.9%. And you think, fantastic, 99.9% good to go. And what the 99.9% actually means is 99% chance the aeroplane will crash if you take off. It can be as basic as this. You can get the model the wrong way up. This happens all the time. You see this with targeting. It's incredibly common that you build a model to rank a set of customers for who are the best targets, and then you start from the wrong end of the list and target all your worst prospects. It's incredibly easy to do. And again, that's a different kind of error of interpretation, an error of interpretation at the output. And it's only if you get through all these stages successfully that you end up with a successful operationalization of your model the first time you put more data through. Now, if you buy into this process at all, you don't have to buy into the detail, you don't have to buy into any of it particular, but if your analyses processes look anything like this at all, what I think is incredibly sobering is to put some numbers on it. Now, I've just made up these numbers. These aren't even measured numbers. These are the most optimistic numbers I feel it's possible to put on this process for anyone I've ever seen doing this. Actually, that's not very optimistic because there are no numbers. So I reckon you're doing pretty well if 80% of the time you don't fundamentally misunderstand something at the start. Maybe you're better than that. Maybe you can do it 90% of the time. Maybe you can do it 99% of the time. I think 80% is pretty good. Not making an important bug, an important mistake, a meaningful, not just some trivial one that gets a decimal point wrong, but a fundamental bug in coding, I think 70% is incredibly optimistic for that. Again, maybe I'm just bad at this stuff, but run the analytical process. Let's assume that you only screw that up 10% of the time, that your data hasn't changed fundamentally 80% of the time, and that you don't misinterpret the results 90% of the time. Anyone think these are ridiculously pessimistic numbers? Anyone much better than this in the room? Don't be shy.
I think they're optimistic.
You think they're optimistic. Yeah, I think they might be optimistic. Like I say, these aren't real numbers. These are like my upper bound on what I think you could reasonably expect. Well, the bad news is that if you do that the first time through the process when you run it, you've only got a 36% chance of getting a right answer. And again, I don't mean it's going to be out in the 5th decimal place. I mean like it might be completely invalid. And the bad news is every time you go around this cycle, you don't redevelop it, but you do run new data, so you get to use the software again, you get the chance for your data to have drifted again, and you get the chance to misinterpret it again. So if you haven't built this into a pipeline, then each time through potentially this, and of course it doesn't drop down mechanically like this, but it does drop down each time. So this is the sort of sobering backdrop to why I think maybe some of this TDDA stuff's a good idea. The bad news is that I'm not going to tell you how to eliminate all these sources of errors or whatever. I'm just going to give you some tools that I hope help you think about how to do it, and some tools that actually help with at least some parts of this process. Okay, so there are between 2 and 2.5 main ideas actually implemented in the TDDA library that we're going to be playing about with. The first idea is the idea of a reference test, and the second one is the idea of constraints. And we're going to go through these in some detail. But very briefly, the idea with reference tests is, for those of you who know about test-driven development, they're a bit like system and integration tests. So the idea is that when we've developed an analytical process of whatever kind, we capture some kind of a test that we can run to check that it's working correctly. And then we rerun that periodically. Like before we use that process again, we check that the test's still passing, that nothing's broken. And we rerun these, in fact, we rerun these tests all the time, basically. Whenever we go to a new platform, whenever we don't go to a new platform, whenever we run it on some new data, whenever night turns to day or day turns to night, we run these tests. And you might think, if you haven't changed your software, you know, how could it possibly fail when it was working before? But those of you who've done this stuff will realize that there are 1,000 reasons why things that work today end up not working tomorrow. Whether it's because you upgraded your operating system, or you changed your version of Python, or you changed one of your libraries, or the operating system upgraded the operating system, or your helpful colleague upgraded an operating system, or there's a Y2K bug and we've just tripped over a day, or a daylight saving times bug, or you know, actually there's disk corruption and your data changed, or there's disk corruption and your code changed. There are a million reasons why these things are not. And that's before you even take it to a different platform. You know, you developed it on a Mac and now you're going to run it on Linux, or you developed it on Linux and now you're going to run it on Windows. All of these things can cause things that work in one place not to work anymore. So it's incredibly useful to have tests that check this. So that's the first idea. And the library has lots of support for writing the kinds of tests that I think are useful in testing analytical processes. And the second idea is the idea of constraint discovery and verification. And these things are a bit like unit tests for data, again, for those of you who know about TDD. So this is the idea of checking that your inputs are the right kinds of inputs, that your outputs are the right kind of outputs, and if you have intermediates, that your intermediates are the right kinds of intermediates using constraint technology. And we'll talk about all of this in much more detail. And I said 2.5 ideas. The third idea, not fully, it's sort of implemented in the library, but not in the constraint bit, is some fancy stuff for characterizing strings with automatically discovered regular expressions. But we'll come to that. So if you haven't done it, you need to have the TDDA library, and you can get, if you're on Wi-Fi and you haven't got it, you can get that in one of 2 ways. You can either just pip install TDDA, or if you want the source, which you're of course welcome to do, you can clone it using that git clone command. My contention is that we've done detailed testing to establish that it runs under Python 2 and Python 3 on Macs, on Linux, on Windows, and under both unittest and pytest. It might be the case that not all of those things turned out to be true when we tried it earlier this week, but I believe it's all true now. As I say, it's MIT licensed, so you can use it for pretty much anything. There is Sphinx source documentation in the doc subdirectory of the source release. There's also a built copy online at pythonhosted.org/TDDA. And there's a quick reference guide, which some of you have, to the 2 main parts, the reference testing part and the constraint generation part here, but also available at that URL there. Handily, the printed version of the cheat sheet has the documentation link wrong. It's actually right in the link, but it's difficult to click the link, it turns out, on a bit of paper. So, but it's updated online. has anyone not got the TDDA library? Does anyone want a minute or two to get that? And obviously, if you are not in a position to type, but you want to buddy up with someone who's got a computer, that would be a good thing to do as well. I think I'm just going to carry on. OK. So reference tests. Let's go through that in slightly more detail. So the idea with reference testing is you already have, when you're doing some analysis, you already have some process for deciding when you're done, right? It might not be a formal process, but you do something, you come up with a result, you don't believe it, you go around, you keep working on it till you've got something you're happy with. And what I mean by done could be you decide to show it to a colleague, you decide to ship it, you decide to commit it, you decide to believe it, you get someone else to believe it, whatever. But you have some process by which you either determine it's not going to work and you stop, or you have some level of belief in it, you're going to start using it in some way, you're going to give it to someone. So let's not change any of that. Not talking about writing tests first or any of that property test-driven development stuff like that. All I'm talking about is you've got some process. What I'm recommending that you do is this. You developed it on some data. Capture that input data, preferably in source control or something, but at least put it somewhere where you know where it is and it's not going to get lost. Capture the output data, the results that were produced, even if that result is, like an ASCII file or a PDF or something. Capture that output. And preferably, capture the analytical process so that the whole thing's in software and you can just run it mechanically and you can set it up so that it reads your known inputs, runs itself and produces the output. If you can't do that, at the very least write down a detailed list of instructions for exactly how to do that. And that is your first test. That is your reference test. So the word reference just, I don't know, it doesn't really mean anything. It's just what we call it internally. But it's the idea of this is our reference whereby we'll know whether the thing's working, at least on the stuff we developed it on originally. Okay, so it acts as a reference for whether stuff's working. And then the idea, as I say, is that you just rerun this thing periodically, and ideally you have some kind of an automated procedure for checking whether the result's the same, so some kind of a diff tool or whatever. If you haven't got an automated procedure for doing that, if it is producing a PDF that you can't diff for whatever reason, then you have to be the tool. You have to look at it and say, is this the same result? And it could be a single number. It could be that all of this stuff takes this enormous amount of data and it's supposed to produce, 42 or 23.4 or zebra or something. Or it could be something bigger than that. Whatever it is, capture it and run that as your test. So that's the idea of a reference test. Is everyone clear what I mean by a reference test? Any confusion, any questions, any?
This is something that you do after you build everything that you do for analysis?
Yeah, I mean, you can do it for sub-bits of the analysis, obviously, and it might be better to do it earlier. But as a sort of minimal thing, what I'm saying is you already have a process for deciding when to stop. Just don't quite stop then. Just spend the extra little bit of time to save away your inputs, save away your outputs, write some instructions if necessary for how to run it again, and then do that, preferably automatically, but if not automatically, at least before you run it again, check it still works on the old thing and produces the same valid result. I mean, sooner is better. Doing it really early on is really good, but that's hard. Everyone finds it hard to do it early, so let's not shoot for the moon. Let's just do the basics.
So
Did you?
This middle bit is versioning your models.
No, not well. Sorry, you mean the capturing of this stuff?
No, yeah.
Yeah, the capturing of it. Obviously, if you then change it, because that's another way things break. People fix bugs. You would not believe how dangerous fixing bugs is. Yeah, obviously, if you change it, then ideally all this stuff should go into version control, or at least the code should go into version control. And certainly you should be versioning it so that if the right answer now changes, so a common thing would be you develop it, you think you've got the right answer, but eventually you discover, either in some very embarrassing way or in some nice way, that actually the answer's not right, and so you fix something and you change it. It's of course a good idea to have that version to update your reference results at that point and so forth. Yes. Yeah.
How do you deal with version control for your input and outputs if they're really large?
Well, if they're really large, then you probably can't. You probably don't want to stick them in version control. One thing to do, obviously, is if you can to use cut-down versions of them. So often, even if the real thing you developed it on was terabytes of data, you can often still form a useful reference test out of some subset of that. If that's not possible, then I guess the thing I'd recommend is that you at least take some kind of a checksum of the things, put that in version control, and then have your reference test be that you first of all check that the checksum's correct on the input data, and that your checksum's correct on the output data, and then you know that you're checking the right thing. You can check that. So if you like, turn the whole thing into a checksum-based thing. Yeah. Yep.
What is this different from normal unit tests? Assume analytic process is like just like a function.
So this is more like an integration or a system test than a unit test. But the whole idea is to take this stuff. The point is not that this is different. The point is that this isn't typically done in analysis, whereas it is often done on the software side. The next part of it, the constraint bit we're talking about, is very different from anything in test-driven development. But this part of it is, it's just I'm not claiming there's anything clever about it. It's just, the goal was, right, to take these good ideas from best development practice and apply them to data analysis. Now, the library does have a whole load of things that make it much more suitable for analytical type tests than traditional tests, because it turns out that typically when we're testing ordinary software, we're checking that a number's right or a couple of numbers are right or something, whereas here we might be checking that an entire data frame's right, or that a graph's right or something. You can't really use the same techniques for that, which is what the library helps with. Okay, so in fact that's exactly what this is about. So the library, the reference test part of the library, has support, amongst other things, for comparing an actual string, one that you've got in memory, a string that you've generated from some process, to an expected string that's in a file. Right? So simple stuff. It also has support for doing things excluding lines that contain particular substrings, or regular expressions. So it's very common, for example, that if you produce, well, almost anything, but particularly a graph, say it might have a date in it, it might have a version number in it, and those things don't make the graph different in any meaningful way. So you don't want a test to fail just because it's got a different version number in it or because it was produced on a different date. So you need this ability to exclude bits and pieces, and it supports that. In fact, it has a more general ability to pre-process the output you just provide a function to manipulate it in whatever way, which could be stripping out bits of it or modifying bits of it or standardizing bits of it or permuting bits of it. It has support for writing out, when a test fails, for writing out the actual result, which was just sitting there in memory, into a file so that you can now diff it against your expected file, and it will tell you what the diff command that you need to run is. It has the ability to check multiple files rather than a single file, or indeed files rather than strings. And it has the ability also to automatically regenerate your reference outputs for you. So once you've verified that you have fixed a bug, and so the correct output is now different, it can rewrite that standard output for you. And this sounds very trivial, but it turns out to be very useful in practice. Now, you have the responsibility for actually checking that the new output is the output that you want. If you just use this blindly, obviously the whole thing will turn to shit very quickly, to use the technical term. So this is for unstructured data. There's stuff for structured data like data frames and things as well, but this is the first part we're going to look at. So I think we're actually at the point where if you don't have a view or don't know about PyTest, just use unittest, because you won't even have PyTest installed. If you prefer PyTest, there are PyTest variants of all the stuff here as well. So the first thing you need to do is, unless you want to try it in your own data, the first thing to do is to get the data. So if you've got the TDDA library installed, go to somewhere that you're happy to write stuff, so a temp directory or just somewhere you're happy to do stuff. And if you run the command python -m tdda.referencetest.examples, that will copy into the directory you're in a copy of the test data and the test scripts in a file, in a directory it will create called reference test examples. So python -m is just saying run the module tdda.referencetest.examples. So that would be a really good thing to do. I can obviously do this as well. I'll maybe do it after people have had a go themselves, so you can see what should have happened. But because obviously it works on my machine, or at least it did earlier. And then when you've done that, the first thing to do is to look at the two results. So we've got a thing called generators.py, which generates two different HTML files, one of which is called stringresult.html and the other is called fileresult.html. So the first thing to do is just to look at those, maybe open them in a browser or something like that, or look at the actual HTML file. They're both just single files. And And then the first thing is so there is a test already written. In fact, there are two versions of it. There's a unit test version and a PyTest version. In the unit test subdirectory, there's one called test using reference testcase.py, and it's probably called the same thing in the PyTest directory, but it's set up for PyTest anyway. You should just be able to run those commands, and you should get some passing tests with, I think, 5 tests that pass. I was going to say I'll do it at the same time, but I guess then that wouldn't be projected, so I won't do that. I'll do it afterwards. So maybe when someone succeeded in doing that and getting the tests passing, you could shout bingo or whatever. And if no one succeeds in making the tests pass, this tutorial's going very badly indeed. It's working? Okay. And have you looked at you should probably look at the HTML, probably in a text editor, but you can also obviously look at it in a browser. It's very pretty, he says. So what all the tests doing is running this generator code, and the 2 tests that are relevant out of the 5 are, one of them generates the string result in memory, so that's one of the 2 web pages in memory, and then the test checks that that's the same as a file, or at least more or less the same as a file. Now it turns out this file includes copyright information and version information that's not the same in the generated code, in the generated page as in the original one, but because we've passed exclusions in, as we'll see, those lines are getting ignored, and it's only checking the semantic differences, if you like. The other one is writing out a temporary file into a temporary directory that the system gives it as file result. And again, it's checking that those up to these rather trivial changes are correct as well. And so that's what this note's about, the fact that we're specifically ignoring, we've actually said patterns, we probably should have said strings, but we're ignoring lines with copyright and lines with version in. We could have been more specific. Okay, I think because we don't have that much time, are people happy if I move on to the next bit now? So the idea now is that we want to invalidate the test. So what we're going to do is we want to make some change to the generator code so that the files that get produced are different. So if you look in generators.py, it's a very simple thing that has got some explicit HTML in it, including this h1 tag, and my suggestion is that you change the contents of that heading 1 by turning it to uppercase or something like that, just making it different so that we get a different result out of the code. So literally open up generators.py in your favorite text editor or IDE or whatever and make some change to the string. So again, I can probably show you this. Oh, sorry, is it more useful if I leave it? Maybe it's more useful if I leave it up. So literally just, make the title, add your name to it, or capitalize it, or change some other bit of it, or something, so that we're going to get the wrong result rather than the right, or at least a different result rather than the right result.
I'm done.
You could unplug. There is one left, actually.
Is it?
There is.
I didn't see that. Cheers.
Okay, and then, whether you use PyTest or unit test, just run the tests again. You should get either 1 or 2 failures. I think if you change both the headings, you should get 2 failures. I guess if you only change one of them, you'll probably only get 1. So it should fail, and it should fail in a fairly helpful way that tells you, if you look at the output, first of all, what the difference is, and secondly, perhaps even more importantly, what the diff command is, hopefully localized for your system. So if you're on Windows, hopefully it'll give you a file comparison command, and if you're on Linux or Mac, it'll give you a diff command to actually look at the differences. And then if you run that diff command, you should be able to see, first of all, the change that you've made to the files or the strings. But secondly, you'll also notice the different versions and the different copyright, emphasizing that those were different originally because you haven't changed those. Yep.
Can I check, is the testing done under unit test? Is that the same as happens with PyTest?
Yeah, they're testing exactly the same thing. It's just one of them, obviously the way PyTest and unit test. I mean, you can use unit tests under PyTest, but PyTest people tend to hate that because unit test's evil, apparently, for reasons I don't understand. But yeah, they're testing exactly the same thing. Sorry, have people succeeded with that? You've got failures? Excellent. So the idea is now that let's suppose that this change that you've made is an improvement. It's not much of an analytical process, but our analytical process of writing a web page, a fixed web page, let's assume that this is the correct output that we now want. The old stuff was wrong, or at least we've decided we want the new stuff. And now we'd like to rewrite our reference output so that when we generate this, we get the right result. And the way you do that is by running, again, depending whether you're using unit test or PyTest. In the case of PyTest, you just add a minus capital W to the line that you use to run the tests, or you can say minus minus write all. And in the case of PyTest, you add minus minus write dash all minus s. And what that will do is that will take the generated output from the test, write that into the area where the reference results files are. And what that means is if you, after having done that, run it with write all, or minus w, and then run it again without the write all or minus w, your test should now pass with your modified code. And again, I can't emphasize enough, obviously, if you blindly do that whenever the tests fail, you just use minus write all you're going to do is gradually write bugs into your testing process. But if you take the responsibility to actually check that it really is the correct result that you want, then this saves a huge amount of time and effort. And in fact, reduces the chances of getting things wrong because the whole thing's automated rather than you depending on actually copying files into place and so on. Okay, hopefully that's incredibly inspiring and you're all going to go off and do this with your unstructured output. I will talk through briefly the same thing for... I'm sure the title for that slide didn't used to be if. Well, there you go. So that's that final bit, just running it again to check that they now pass. Okay, so we have exactly comparable things for structured data, right? Not just for generating a blob of text, but for generating either the two specific examples this supports are a data frame or a CSV file. Now, CSV files, obviously you've got all the problems about CSV file formats and so on, but it will read a lot of CSV files sensibly. You might have to make some changes if you have a weird CSV format. So with structured data, the equivalent stuff is we want to be able, so what the library supports is comparing a generated data frame or CSV file to a reference data frame that you've got or a reference CSV file. Again, it will show you the specific diff command that you need to use to see what the difference is if they're not the same in the case of the files. You can check multiple CSVs at the same time and it will show you all the errors, not just the first one. You can specify a subset of columns to check, so it may be that there are some columns that have got random numbers in it or that you're not expected to be the same or that you don't care about. You can choose whether you want it to be very picky about types or not. Generally being very picky about types with pandas is not fantastic in my experience, but you can be. You can choose whether you care about column order, so if the thing that you're testing has the columns in a different order, do you regard that as a problem or not? It's up to you. You can choose to ignore the actual data values and only focus on the types. You can choose the precision for floating point comparisons. And again, it's got the automatic rewriting behavior. Now, obviously, all this is documented in the full documentation. We're obviously not going to go through all these variants. And in fact, I think given time, I mean, these are the 4 calls that you need. Again, these slides are available. So there is a comparable exercise you can do. I mean, it's very similar. We can... If you succeeded with the other one, you could do it very quickly. It's just so you've already got this data. If you go into the reference subdirectory, you should see dataframe result.html. I think that's .csv, not .html. Yep. it's amazing. You see, you can come and talk about testing and getting things correct, and illustrate the impossibility of it by your own incompetence. Sorry about that. I'll update the slides afterwards. I mean the online copy of the slides afterwards. So this is a tiny data frame that's being generated. Again, you can run it and it should pass. You can look at the data frame by running that little command. And so the idea here is it generates a bunch of things, including a string column called S. And the string column called S writes one of the floating point numbers out to a fixed number of decimal places. And you can specify it. There's a precision parameter in the dataframes function or the dataframes file that specifies how many places to write it out to. So if you change that default behavior, obviously you'll get a different string column, which means that the test will fail. So if you do that, if you open up dataframes.py and change that default precision from 3 to 2 or 3 to 7 or whatever, it should the test should start failing. 3 tests should fail because the same function is used to generate 3 different data for 3 different tests. And then again, if you do the minus write all minus S in the case of PyTest or the minus capital W in the case of unit test, it will rewrite those reference results for you and everything will be good. So again, because time's short, I think I won't give you a lot of time to do that, but you get the idea. Basically, this thing supports both structured data and unstructured data. In the fullness of time, maybe it'll support JSON and other things as well, but at the moment, that's the basic scope of the thing. And we have found it incredibly helpful. We use this all the time as an augmentation of unit test or PyTest. Yes?
If you test on data frames, you always store them as CSV, or do you pickle them?
You can do what you like. No, so you have the option of just pickling them and storing them, or in fact, we also have support for storing them as feather files. For those of you who know about feather, so feather is a library written by Wes McKinney and Hadley Wickham, who's one of the R-stars that allows data frames to be shared between persisted to disk and written from and read by both Pandas and R, including type information and so forth. So that's another good way of doing it. Obviously CSV is the worst possible thing to use. It's just that it's incredibly common, so we support that. But no, you're much better either pickling it or using feather or something like that. Okay, let's move on and talk about constraints.
Sorry.
Yes.
Support for HDF5.
No. But if you wanted to add support for HDF5 and do a pull request, that would be awesome. Okay, constraint generation and verification. So, constraints. So, hopefully you'll agree that it's fairly common for data analysis to use data tables in some way. You know, data frames, whatever you want to call them. Tabular data with like columns that have meaning and types and rows that are different values. Either as inputs or as outputs or as intermediates or all of those things. Certainly a lot of the analysis we do is like that. There are obviously other things like, you know, JSON, XML and binary data and so forth, but this is incredibly common. And there are probably lots of things that we know ought to be true about that data. And so what we could do in principle is we could write down all the things that we think ought to be true about that data and we could check them. And the only problem with that is no one can be bothered. I certainly can't be bothered. And even if I did, I wouldn't think of most of the things and I'd probably get them wrong. Life's too short. So the big idea with the constraint stuff is instead of us writing down the stuff, let's get the computer to figure out what constraints are true about one or more specific data sets that we use. And these can be input data sets, these can be output data sets, or they can be both. And ideally it should be all. We should be doing this at all stages through the analysis. Let it write out a set of constraints that were true of the data we built the process on, and then check whether they're true. So we have what we call a discovery phase, where given some data sets, it writes a set of constraints for you, it writes them out as a JSON file. And then a verification procedure that checks that some potentially different, typically different data obeys those constraints as well. Now, of course, the constraints won't always be obeyed by the next set of data because no two data sets are the same. But the idea is, even though almost none of us can be bothered to write down a whole load of constraints, maybe we're willing to look at the 2 or 3 things that fail next time we run it because, customer number is now bigger, or date is, the biggest date in the data set is now bigger than it used to be. Well, the date's later. Of course the date's bigger, so maybe that wasn't a good constraint to write in. Though maybe we still don't want the date to be, further ahead than 2050 or 2500 or something, or the day after tomorrow. Or indeed today. Maybe we don't want it to be bigger than today's date, whatever today's date is, a variable date. And so that's really the big idea. So let's look at some examples of this. So here are some example constraints that might be true. If we have an age field, probably we'd be suspicious of ages more than 150, notwithstanding the guy who died the other day who was apparently 155, I think it was. But no birth certificate to prove it. We might want the type of our age to be an integer, or at least to be a number. If we've got a customer ID, we might not allow that to be null, at least in a master customer table. We might want, in a master customer table, all customer IDs to be unique, i.e. never to have any duplicates of those things. If we've got a credit card number, we might want it to have 16 digits, and so on and so forth. So constraints on single fields. We might also have constraints on whole data sets. So maybe the data set should contain a field called CID. And maybe it should have a particular number of records. It should have exactly 118 records, for example. Maybe if we've got tagging on fields and things, one of the fields should be tagged with an O, and maybe exactly one of the fields should be tagged with an O. Maybe it should be sorted in date order on some date field. And there might also be multi-field constraints. So if we've got a start date and an end date, maybe the start date is not supposed to be later than the end date. That would be quite a sensible thing. Maybe if we have things representing force and mass and acceleration, and we believe Newton knew what he was talking about, then pretty much F ought to equal ma, since that's a universal law outside the quantum and relativistic scopes. Lots and lots and lots of stuff like this that we could write down. So the kinds of constraints currently supported by the TDDA library are minimum values, maximum values, signs as well. Now, obviously, the sign of a number is fully captured by the minimum and the maximum, but we think sign is so significant that even if you end up with a smaller minimum than before, it's probably significant if it's negative where it wasn't before. So we separately capture constraints about the sign. We look at whether a field is null or not. We actually capture it as the maximum number of nulls allowed in a column, but typically that's either 0 or the constraint's not there. In other words, what you're really saying is this is not a nullable field. We detect whether there are duplicates in fields, i.e. repeated values, particularly for string fields, but for numeric fields as well. In the case of strings, we calculate the minimum string length and the maximum string length. Oh, I've missed one out. We also, for categorical looking fields with not very many different string values, we capture the list of values that are allowed. And although it's not implemented on the master branch, we also have an ability to generate regular expressions to characterize fields and use those for verification. That's the RexPy thing that I'll talk about at the end if we don't run out of time. It is included in the library and it is available online, but it's not used right now for this discovery and verification process. But when we release version 0.4 of the library, which might be within the next few days, that will become available. Not all of the constraints apply to all field types, but column types, but many of them do. So we have a similar sort of exercise we can go through. So again, if you go to some area where you are happy to write a new directory, your temp directory or whatever, and you run python -m tdda.constraints.examples, that will copy a directory called constraints examples into your directory. And that will include 2 CSV files containing one called elements92, which contains information from Wikipedia about the first 92 elements in the periodic table, that is everything up to uranium, and also elements118.csv, which contains information about the first 118 elements of the periodic table, which is all of them that had numbers a few years ago. I think we might be up to 120 odd now, but they're pretty uninteresting. And then you go into that directory. So you should see in that directory, as I say, elements 92 92.csv. No, it's probably in, it's either there or in a subdirectory. I think it might actually be in test data. And if you run Python elements discover 92.py, or, now that's the other thing. When you install the TDDA library, as well as installing like the library itself, it installs a TDDA command for you that you can use. And so this TDDA, in fact, the simpler thing to do, and the thing that I'd recommend that you do, is actually run the second command there, TDDA discover test data / elements 92.csv elements 92.tdda. And what that will do is it will run its discovery process over the first 92 elements of the periodic table. So it will read them into a data frame using the CSV reader. It will then generate a set of constraints based on the first 92 elements, and it will write them out as a JSON file called elements92.tdda. And it will look like that. So this is saying Z, which is the atomic number, is an integer field. It has a minimum value of 1 and a maximum value of 92. It's always positive. It doesn't have any nulls. And it doesn't have any duplicates, which, of course, you should read as this field has to be an integer field. The smallest value it's allowed is 1. The largest value it's allowed is 92. It must always be positive. It mustn't have any nulls, and it mustn't have any duplicates, and so on down. So you see there are various other things. We've got some string ones with, for example, the allowed value for chemical series. It noticed there weren't very many different ones, so it's actually listed those out, and so on and so forth. So have people succeeded in running that and getting that elements 92 generated? No. Has anyone succeeded in running it?
Yes.
Ah.
Missing import.
Missing imports.
Level TDDA dependency.
Feather. Ah, Feather. You have to install, yes, you probably have to pip install Feather format. Sorry about that. Wow. Shit testing, you see. That's the great thing about having a whole lot of people in a room to test your software for you. Apologies, yes. Is it pip install Feather dash format? Yeah, sorry about that. I will type that on the slide. That should be a conditional import, of course, but apparently it's not. Okay, that will make that work. Sure. Okay, so if you have a look at it, you see that JSON. So now the interesting thing to do is to, well, so the first thing is to verify that the data set you generated those constraints from satisfies it by running the TDDA verify command. So again, I'd recommend the second one, this TDDA verify test data / elements 92.csv elements 92.tdda, i.e. verify the very same CSV file that you generated the constraints from with those constraints, and that should obviously pass. You should get, I forget what number, 67 or 72 passes or something. Some number of passes. No fails is the important thing. Now, and in fact that's what I get. I get 72 passes when I run that. And obviously the ticks are the passes and the crosses are the fails, and there aren't any fails, so that's good. So now we can try and use those same constraints to see whether the full data set, the full 118 elements, satisfy the constraints as well. And what we expect is they won't, because after all, one of the constraints that got generated was the atomic number shouldn't be bigger than 92. And of course, in the first 118 elements, of course it is bigger than 92. It goes up to 118. So if you run exactly the same verify command, but now using elements118.csv rather than elements 92.csv, you should get, I think it's 5 failures. And so some of those are to do with maximum and minimum values. I think some of them are also to do with nulls. There are nulls in the bigger data set, whereas there aren't nulls in some columns in the smaller data set. And then really all that's left is to, there's, I think included in the data, there's a elements 118.tdda, which I previously generated, but you could generate yourself if you want to, that is the constraints generated from the larger data set. And what you should find is that if you verify the larger data set against that, it passes, but also that if you verify the 92 data set against that larger 118 set of constraints, those should pass as well, because of course the constraints that were true for, doesn't quite follow, but it pretty much follows that the ones for the 118 are bound to work for the 92, and indeed they do. So I'll give you a minute or two to do that, and then we'll carry on. Obviously anyone shout if there are questions or whatever. I guess I'm hoping what, clearly to some extent you're just typing, you're not not really doing that interesting stuff here, but I hope what you're getting is the idea that these constraints are useful, and that if you, yes, you'll have to edit them, you'll have to edit that JSON file and either change them by hand sometimes or delete them when they're not relevant. But the idea is if you have a process that you run every day, and you first of all generate the constraints the first time, you look at them, maybe you take out the ones that don't look sensible, or you modify the ones that don't look sensible, and then every time you run it, you see whether there are failures. If there are failures, you look at whether they're failures you care about that indicate there's actually something wrong with your input data, or your output data, or your intermediates, or you discover that actually that's perfectly fine, that's a constraint that shouldn't have been there, and then either you modify the constraint or you remove the constraint. You end up with a very useful set of constraints. And you can make those even more useful by generating extra check columns that are exactly things that you've put in specifically to check that they, because they should be true, they are true. So for example, if you have a set of fields that are supposed to sum to another field, or if you have a set of intermediate results that are supposed to sum to a grand total, maybe you want to put the intermediates in and check that those things are true. Or explicitly put in a difference column and make sure that that column is always 0 and stuff like that. Those can be very powerful ways of implementing other data sanity checks that you might want to do within this same context of this thing, just by writing extra columns into the data that represent things that either should always be 1 or should always be 0 or always true or always false, or never longer than 10 digits or whatever it happens to be. Okay. So we've done quite well on timing, because that was what I figured we might get done. That might just mean, of course, that I rushed through it far too quickly and you're all completely bamboozled. But it does at least mean we can talk a little bit about RexPy, which I think is quite exciting. So let's talk about that briefly. Here's an example of a successful verification with failures. Here's an example, unsuccessful verification. Oh, and here's the other thing. You'll all know, because you'll know Mark Haddon's book, if nothing else, The Curious Incident of the Dog in the Nighttime. So in Silver Blaze, there's an interesting part in the book where Gregory, the Scotland Yard detective, says to Holmes, "Is there any other point to which you'd wish to draw my attention?" And Holmes says, "To the curious incident of the dog in the nighttime." And Inspector Gregory says, "The dog did nothing in the night time." And Holmes says, that was the curious incident. And of course, what that proved, as you'll instantly have recognized, is that the perpetrator was obviously known to the dog, and therefore the dog didn't bark because it was a known perpetrator, and that proved that the butler did it, or whatever it was. When you generate these constraints, it's very tempting to look at the constraints and say, do these make sense? But it's very important to look for the constraints that don't get generated as well. So, you have a field that shouldn't be null and it doesn't generate a constraint that says it shouldn't be null. Well, that means you've got nulls in that field. You generate a field that should be unique for every record and it doesn't generate a constraint that says it's unique for every record. That's telling you that you've got duplicates. I mean, not that these are hard things to find anyway, but again, this is a very easy mechanism for producing these things, and as you look through them, it's the figure ground thing. It's important to look at what's not there as well as what is there, because very often that's every bit as significant. Okay, so let's. That's the API. You can look that up in your own time. It's a beautiful API, and that's. Oh, the other thing is when you do a verification, as well as just printing textual output, it can produce a data frame with that verification in it, which has one row for every column and one column for every constraint type, and then they're true if the constraints pass, false if the constraints fail, and none if there was no constraint to be checked for that case, because either it didn't apply or there wasn't a useful thing discovered. And obviously you can write if you really want to, you can write your own TDDA files by hand. Wouldn't recommend it, but but you can.
Sorry, can you go through the first line? Atomic weight, failures 2, path 3, type true, min true, so there's no minimum length?
No, I'm sorry. What this is saying is that when we ran this verification, some particular verification, it's saying that there were 2 failures for the atomic weight field and 3 passes, that the type constraint passed,
Okay.
that the min constraint passed, that there wasn't a min length field, min length constraint because it's not a string field, so you don't get a min length constraint, that the max failed. So this is probably when we verified against 118, and the max was higher in the 118 dataset than the other dataset. There was no max length constraint, again, because it's not a string field. The sign constraint passed. The max nulls constraint passed, so that means there were nulls in the in the atomic weight when there was a constraint saying they weren't allowed to be. And there was no duplicates constraint and no allowed values constraint. Does that make sense? It can be a little bit confusing, but true means the constraint passed, false means the constraint was violated, failed, and null or not a number means there wasn't a constraint to validate in that case.
These are the predefined constraints rather than the user-defined constraints.
Well, no, it's whatever you're verifying against. So this is when you run a verify, it produces a verification object. That verification object has a toFrame method on it. That toFrame method produces a data frame with 1 row per column, and a column for each constraint. And it's whatever it is. You could have written them by hand, or they could be from the discovery process, or whatever.
Okay.
Yeah.
Okay.
Yes.
Is there an automatic way of combining 2 sets of constraints?
No, there isn't at the moment, but that is obviously an extremely necessary thing, and that is something we will be working on. And if you were to write such a thing, we would love that pull request, but we will do it anyway. If you even just put in a change request against the repo for that, that will encourage us to do it, because it's obviously a useful thing. Yeah.
You mentioned about multiple constraints or mixed constraints.
Yes.
Is this covered in some way? Or?
So, as I mentioned, we're a commercial software house and analysis house as well as this. So what we tend to do is we tend to implement things in our software first as a sort of rough and ready version that's useful, and then we try and learn all the lessons of that and put it into the nice open source framework. So we have the multi-field constraint stuff in Miro, our software. We haven't ported that to the thing yet, but that will definitely come to this. The whole dataset constraints we mostly haven't even got in Miro at the moment. We have got the regular expression stuff, and as I say, the regular expression, all the basic regular expression capability that I'm about to talk about is in the library as well. It's just not actually, well, in fact, it's on a branch in the code as well, but it's not tested enough to have wanted to push it yet. So that will come again. So, in fact, TDDA futures, there you go. Though it doesn't include the one you asked about, which is important. So the immediate future is RexPy, which is what I'm about to talk about, which is automatically discovering regular expressions to characterize string fields. Join keys are important, so multiple dataset things where you should have particular kinds of relationships between keys in different columns is a good thing to test as well. There's a very obvious thing that we haven't really done much work on yet, which is characterizing distributions. So not, simple mins and maxes and things, but what is the general shape of this distribution, and does it look like it's changed? Both first order and higher order things. So what's the one-dimensional shape of this distribution, and what's the multi-dimensional shape of the distribution? That will take a bit longer. Nearly constraint discovery. One of the limitations of constraint discovery is that it's all or nothing. If you have a single negative value, it's not going to generate should be positive constraint, but it obviously would be possible to say this constraint's very, very nearly true. Maybe it's supposed to be true, and so that's a thing we'll look at. There's obviously more and more JSON data in the world, so we should maybe think about that and think about JSON schemas as part of that. And there are lots of other things, including combining constraints. Here's the first final slide, which gets repeated later, because I thought this might be as far as we'd get. But we haven't. We can talk about RexPy. So, who knows about regular expressions? Anyone not know about regular expressions? Seriously, does everyone know about regular expressions? That's fantastic. So you already know the joke, right? Some people think, when they have a problem, I know I'll use regular expressions. Now they have 2 problems. Regular expressions are incredibly powerful. You all know what they are, so I'm not going to talk it through. They're a complete pain to write, but they're very good. And they're, clearly given a bunch of string data, It would be nice if something could come up with a regular expression or regular expressions that characterize that accurately for you. And that's what RexPy is all about. I should emphasize it's not intended to do completely general text. I mean, it will work on completely general text, but it's intended for the sort of text that you typically get in string data in structured data sets. So, it's string identifiers and things with obvious structure. It's not trying to write regular expressions for English language or Hungarian language or, random crap. It's stuff with some structure in there that it's trying to find. So, telephone numbers and postcodes and zip codes and, the sort of stuff that you actually like to find. So, pros and cons of regular expressions. Well, obviously, they've got the pro of being powerful and sort of ubiquitous, and the con of being ugly and hard to write and even harder to read and even harder to debug and unbelievably hard to quote and escape, though at least in Python we have R strings, which if you don't know about them, you should absolutely use when you're using regular expressions because they make dealing with the backslashes a lot easier. Some of you will have seen verbal expressions, which were a craze about 2 or 3 years ago, where everyone was trying to get away from writing literal regular expressions by using constructors like this. Within the space of about 3 months, they got written for every language under the sun, and I have never seen one used in my whole life in reality. We all just write the regular expressions. So why not let the computer do the work? So RexPy it's an early attempt. It's far from perfect. It's entirely heuristic. But it's a thing that you give it a bunch of strings, and it will return one or more regular expressions that characterize those strings. It's not particularly good at collapsing multiple ones down at the moment. I mean, it could do it mechanically with alternation, but it's not necessarily particularly good at really seeing, this one's that one with just a bit more on the end, but we'll get better at that. So there's an online tool at rexpy.herokuapp.com that lets you paste in a load of strings on the left and get your regular expressions out on the right. You have you can choose whether or not it anchors them, i.e. whether it puts an up arrow at the start and a dollar at the end. And you also have the option of getting it to put capture groups in, i.e. the parentheses, to let you pull out the individual bits. And what it does is it puts capture groups around all the bits that are variable in the string and doesn't bother in the bits that aren't variable, that are just a common thing. So i.e. all the bits you might reasonably want to pull out. So it's available online. It's got a limit of, 1,000 or 10,000 records or something, just so you don't kill our server. But it's also available as part of the TDDA library. This is the help for it. So there's a RexPy command that you should have available. So if you've got the library, if you just type RexPy and then type in 3 or 4 strings that have got some structure, it should spit out one or more regular expressions that characterize those strings. And my contention is that it will always produce the right answer, or at least a correct answer, but it won't necessarily produce an optimal answer. In fact, it's not even trying to produce an optimal answer. It's entirely heuristic. So there's a command line version. There's also obviously an API for generating this. There are various options you can put in to say whether it should, what it should do with underscores and what it should do with dots and things like that. And to say whether you want the capture groups and whether you want the anchors. And there's a pretty simple API for using it. So if you do the same thing, if you do the example thing, if you do python -m tdda.rexpy.examples, again, it will produce a directory for you called probably rexpy-examples. And there are simple programs in there for, again, just with trivial numbers of strings, but it works with quite big sets of strings as well. It will also work with string columns in DataFrames, so you can just give it a column from a DataFrame and it will work directly from that. And so very soon it will use that for the constraint generation and the constraint validation as well. That's an example of doing it in Pandas. So again, I think reading this on the slide's probably not very interesting. And I think that'll do, because it's pretty hot in here. I'm happy to take questions. I'm happy to talk about things. I'm happy to look at examples. I would encourage you all to try this stuff. We find it's incredibly helpful for getting better quality analysis, all 3 of the bits. By all means, come back to me with any feedback directly. There's a blog at tdda.info that talks about the development of this. There's the source code on GitHub. Do log bugs, do log change requests, do pull requests if you want. There's a Slack group that if you tweet me or email me, I'll add you to. It's incredibly quiet, you won't get bombarded. Weeks can go by without anyone saying anything on the Slack group, but then sometimes there is. There's a Twitter account where we tweet about all this shit, and the slightly buggy version of the slides that we started with are online at that URL, but within an hour I will have pushed the slightly corrected and enhanced versions to that same URL. Thank you very much all for coming. I really appreciate it. I hope you all got something out of it. I really think this stuff is useful. We do it for real. It has helped us. It has helped our clients. I think it will help you if you do it as well. Unless, of course, either you're infallible, in which case you don't need it, or you already do all this stuff anyway, in which case I don't know why you bothered coming. Thank you very much, genuinely.